Hi guys, here's video 4-3 for Thursday, December 1st. There's going to be no homework that corresponds to this. And before we start, I'd like you to write this table down. CD and CU. CD stands for concave down. CU stands for concave up. And a section of a graph will be concave down if the slope, or the slope of the tangent line is what I mean by slope here. If the slope of the tangent line is decreasing, and it will be concave up if the slope of the tangent line is increasing. And what's another name for the slope of the tangent line? The derivative. Okay, so if the derivative is decreasing, then the original function is concave down on that interval. And if the derivative is increasing, then the original function is concave up on that interval. Okay, so we're going to draw four sections that each represent like a different concavity situation. So concavity, you are given a section of a graph over a certain interval. State whether the graph is concave up or concave down over this interval. And you should have your transparencies to help you. Okay, so we're going to do the first one here. Imagine the left side of a downward facing parabola. Okay, so kind of like that. Okay. And then here we'll imagine the right side of an upward facing parabola. So like that. And then let's do the right side of a downward facing parabola. And then here let's do the left side of an upward facing parabola. Okay, so for this first one, I've got to ask myself, over time, as I move along the graph from left to right, is the slope of the tangent line decreasing or is it increasing? If it's decreasing, then the graph will be concave down. If the slope of the tangent line is increasing, it will be concave up. So I'll start here. Right now I've got a positive slope, and as I move along the graph, it's still positive, but it's getting less positive. Okay, it started positive and now it's getting less and less positive, so closer to zero. So if a positive number is getting closer to zero, then that means it's decreasing. Okay, so here the slopes of the tangent line are decreasing over time. So this is a concave down segment. Now the next one, we'll start here. Again, it's positive. And now as I move along the graph, so it starts out positive, and as I move along the graph, it's getting more and more positive. So it's getting positive and further from zero. So positive and further from zero means increasing. So the slope is increasing, so this would be concave up. This next segment, all right, now this is a decreasing tangent line. Okay, right there it's a decreasing tangent line, so we've got a negative slope pretty close to zero. And as I move along the graph, it remains negative and gets further from zero. So negative and further from zero is decreasing. So negative and further from zero is decreasing. So concave down. And then this last one here, you probably have already guessed, but we start with a really, really steep negative number. Okay, a very steep negative number. So, or a very huge negative number. So very far from zero and negative. And then as we move along the graph, it's still negative, but getting less negative, so closer to zero. All right, so negative numbers getting closer to zero, that sequence of numbers would be increasing. So this is concave up. Okay, now that brings us to inflection points. An inflection point of a graph is a point at which it changes concavity. A lot of the graphs we're dealing with, guys, won't just be concave up or concave down. There will be changes in concavity, and those changes will occur at inflection points. At this point, the graph could be changing from concave up to concave down, or from concave down to concave up, all right? What we're going to do down here is mark the inflection points below and indicate the types of concavity on either side of the inflection point. Okay, so this first one, and you might even just be able to see it with your eyes, guys, but I'm going to use the transparency just to emphasize it. So I'll start on like this side of the graph here. And this side of the graph, I've got my tangent line. And as I move along the graph, the slope is increasing. Okay, so this is an increasing slope. So increasing, 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 the slope is. And then right about here, it changes from increasing to decreasing. So if the slope changes from increasing to decreasing, that means a change in concavity. So right there seems to me about where the inflection point is. And on this side, it is concave up. And on this side, it is concave down. Okay? And if that doesn't make sense to you, that that's concave up and concave down, then look back at the stuff we just did and try to have that make sense to you. Okay, next, I'm starting up here. I've got a negative slope getting more negative, so a decreasing, 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 and then about there it changes from decreasing to increasing. So about there is, I think, the inflection point. And it went from concave down to concave up. Last one. Okay, I've got a negative slope that changes from negative to positive, so increasing, 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 and right about there, I think, it starts decreasing. And a lot of you can probably see this without using the transparency, which is great. I mean, that's the goal. So concave up to concave down. So those are inflection points. Okay, now, so this next one, we're going to talk about extrema. Okay, so extrema means maxes and mins. Okay, extrema just means maxes and mins, but extrema could mean a max or a min. And so we're going to look at this graph here. This graph has endpoints. So there's no arrow, so this graph starts here and it stops there. And along the way, we have what are called relative extrema, sometimes called local extrema. And what that means, if something is a relative extrema, is that it's not the highest or lowest point overall necessarily, but it's the highest or lowest point of all of its neighboring points, like the points that are right around it. So, relative maxima. So for relative maxima, we're going to be looking for points on the graph that are, hi Loz, points on the graph that are higher. They have y-coordinates that are higher than the neighboring points around it. Okay, so for maximums, I'll be done real soon, Loz. So here is the first one that I see. All right, I'm going to go like this. So if you just look at like the section of the graph, like where I put those little marks, this point here has the highest y value of all the points that are around it. So we've got a relative maximum at f, so it's f of negative 6 equals 6. And the answer is the output, guys. 6 is the maximum, but we want you to write it like this so that we can see the x value that it occurs at. So by writing your answer like this, you're telling your reader that this relative maximum value occurs at the x value, negative 6. Okay, and then looking at the graph, I see another relative max up here. Okay, because if I look at a neighborhood of points around that one, this one is the highest, has the highest y value among them. So f of 6 equals 15. Now relative minima. So I'm looking for a point that has the lowest y coordinate of the ones around it. And I see this one here. Okay, so if I look at all those points around it, this one has the lowest y value. So f of 1 is negative 5. Now, and I'll tell you why I'm asking this in a moment, but endpoint output. So we've got two endpoints to this graph, and here we're going to say their outputs. So the leftmost endpoint has an output at the x value negative 10 of negative 6. And the right endpoint, f of 11, has an output of negative 4. And the reason I did this is because absolute maximums and absolute minimums are different than relative maxes and mins, in that here we want the highest or lowest y values overall. Okay, so a relative max or min could be an absolute max or min, but it might, just because it's a relative max or min doesn't mean it's the highest or lowest point overall. It could be one of the endpoints that is lower or higher. So to figure out the absolute max, we look at the endpoint outputs. We compare them with the outputs at these other points. Well, I guess we would just have to compare with the maximums. So you compare the endpoint outputs with the relative maximums, and then you see what's the highest. And it's this one, f of 6 equals 15. So f of 6 equals 15. This is both a relative and an absolute max. Okay, now absolute min. We're going to compare the endpoint outputs with the relative min. So we've got negative 6, negative 4, and negative 5. Negative 6 is the lowest, so f of negative 10 equals negative 6. This was not a relative min, all right, because at an endpoint, you can't take a neighborhood like I did here at an endpoint, because there's like nothing off to one side of it. So yeah, but for absolute max and min, endpoints could be, could work. Inflection points, I'm looking for a change in concavity. I'm just going to do it fast in the interest of time, but it's this point right there. Okay, and take a moment to think about that if that's not clear right away. So 3, 6, that's the inflection point. Okay, now analyzing a derivative graph. Very often you're going to be given the graph of a derivative, and you're going to be asked to use the graph of the derivative to say things about the original function. Okay, so here, first we're going to determine the critical, well, let me read this. The graph of the derivative f prime of a continuous function f is shown right here. So that's f prime's graph. Determine the critical numbers of f. Well, the critical numbers of f, guys, if you remember, are where f prime equals 0 or is undefined. If I look at the graph of f prime, I see no places where it's undefined, but I see 3 places where it's 0. So I'll say here, f prime of x equals 0 at x equals negative 3, x equals 1, and x equals 4. So those would be the critical numbers. And why are they important? They are important because they are the potential places where maximums and minimums would occur. Now, part B, on what intervals is f increasing or decreasing? Okay, now I'm going to show you guys something that you don't have to write down yet, but we're going to memorize this. When I went to that workshop over the summer that I keep talking about, there was this woman named Susan there who has her students memorize this chart. And I had my own chart just last year that I used it. But it was much more complicated than this. I like Susan's chart, or I called it a table here, much better than what I was using. So I'm going to switch to what she's using. And what she does is she has them go f, f prime, f double prime. And then each row, the things in each row are like the stuff that happens simultaneously. So if f is increasing, that means f prime is positive. If f is decreasing, that means f prime is negative. Any extrema of f will occur where f prime has a sign change, where it goes from positive to negative or negative to positive. Okay, and then we'll talk about the rest later. But this is what we're interested in today. You don't have to write this down. I think next lesson we will. But so this is asking us on what intervals is f increasing. Well, if f is increasing, then so is the tangent line to any point, that touches it there. So if the tangent line is increasing, then that means that the slope of the tangent line is positive, which means that f prime is positive. Okay, so f is increasing when f prime is positive, right there. Okay, so I'll just go like this, increasing, and you've just got to find where f prime is positive. This is the graph of f prime, so where is it above the x-axis? Two intervals from -3 to 1, union from 4 to infinity. So f is increasing on these intervals because its derivative graph is positive on those intervals. Decreasing is going to be just the opposite. If a graph is decreasing, then the tangent lines on that part of the graph are also decreasing. So the slope of those tangent lines is negative. So f prime is negative. So decreasing where f prime is negative from -infinity to -3, union from 1 to 4. Okay. At what x values does f have a local maximum and or minimum? All right, well, right here in Susan's table, we can see that any extrema, an extrema could mean a max or a min, but any extrema are going to occur where there's a sign change. Okay, so if f prime goes from positive to negative or vice versa, that's a sign change. That means we have a max or a min. So at each of these three critical points or critical numbers, there's a sign change, negative to positive, positive to negative, negative to positive. So I know I have extrema at all of these points, but which are maxes and which are mins? Okay, so at what x value does f have a local max? So I'll just say let me just tell you what it is, and then I really want you, there's no homework, so I want you to think about why. All right, so yeah, let's actually have that be part of the homework. Okay, so I changed my mind about no homework. Okay, so back up here, homework, explain my answers to part C. Okay, so that's the homework, is to explain my answers to part C. So I'm just going to give you the answers. Local max, okay, let me think. Local max at x equals 1. Okay, and you explain why for homework. Explain for homework. Okay, and then the other part of the homework will be to explain this. Local mins at x equals -3 and x equals 4. And please put a lot of effort, into trying to do this, guys, because I'd like you to share tomorrow. Explain for homework. Okay, so that's it for the video. I changed from no homework to homework, but it's very, it shouldn't take you long at all. Just give it your best shot at explaining my answers to part C. Okay, so I will see you soon. Have a great night.